k1 plus 5k2, and C will be 3k1 plus 6k2. And then translating that, unknowns, the unknowns are k1 and k2. So we can set up a system with 2 unknowns and 3 equations, and we can compose that little matrix there and then use Gaussian elimination. I want to know, when is this system consistent? When is it not inconsistent? And it's inconsistent. The last row will give me a clue. It will be inconsistent. Well, it will be consistent if this expression is equal to 0. So all I do to pick a vector outside of the span of S is just pick a vector that will make the system inconsistent. And I do that by simply picking this vector here, where that is my value for A, that is my value for B, and that's my value for C. Okay, so if you make A1, B and C are both 0, then this last row it is going to be a problem. It's going to be inconsistent. So picking the vector 1, 0, 0 is outside of the span it's outside of the span, and you can go and verify that that is a linearly independent set. And by the plus-minus theorem, if you have a linearly independent set and you have a vector that lies outside of the span of that linearly independent set, then I can throw that vector in, that vector that lies outside of the span, which is this one, I can throw it back into the set to form this set here, and that set will be linearly independent. So now I've got a set of 3 vectors that's linearly independent, and in a finite dimensional vector space I only need to check one of the 2 properties. So it being linearly independent is enough. Okay. All right, let's look at the third one. It's very similar to the second one. There you asked to use those 2 vectors to construct a basis for M22. M22 being all the 2 by 2 matrices. Okay, so how do we do this? We need to find a vector. We need to first see what the span of S looks like, and then we're going to pick a vector outside of the span of S and add it to S. Right, so we take S and we find the span of S. So if we pick a vector, and let's call that vector A, B, C, D, and now we say that this vector is in the span of S, meaning that it is a linear combination of the other 2 matrices. Okay, and basically we set up a system of equations, and you're going to get 4 equations with 2 unknowns, and you're going to set up your matrix, which is going to be this matrix here, and then again you're going to use Gaussian elimination, and a Gaussian will give you this matrix here. Okay, so now this gives me a clue as to what vector I need to pick so that it is outside of the span of S. So you need to pick values for A, B, C, and D. And a value that can work is we can take the matrix where we pick A as 1, we pick B as 0, we pick C as 0, and we pick D as 0. And that will make this last row inconsistent row, and therefore this vector is definitely not in the span. It's not in the span. It's not in the span of S. Right. Now, just a side note, you can also check that the 2 vectors in S, which are these 2 matrices here, you can also show that they are linearly independent. So by composing this equation, you can see that 0k1 plus k2 is equal to 0. So K2 is 0, and you can also see that K1 times 0, K2 is equal to 0, so K2 is 0. So that's a linearly independent set. So the plus-minus theorem says the following. The plus-minus theorem says that if you have a vector outside of the span of a linearly independent set S, then I can throw that vector into the set S, and I'm still going to have a linearly independent set. So this is a linearly independent set. Now, what is the dimension of M22? The dimension of M22 is 4. So I'm still short one vector. So I need to take this linearly independent set, the new linearly independent set, and I need to further extend it. Alright, so there's my new set S prime. It's got 3 vectors. It's linearly independent. Now I need to go through the process again. I need to pick another vector that's outside of the span of this set. Don't have to check linear independence. I know it's linear independent by the plus-minus theorem. So let's determine the span of S prime. So now you pick a 2 by 2 matrix. Again, you take the 2 by 2 matrix A, B, C, D, and see what needs to happen for this to be in the span of S prime. Okay, so you're going to set up a system of equations. How many unknowns is this equation going to have? It's going to have 3 unknowns. What needs to hold for A, B, C, D to be in the span of S prime? We need to find K1, K2, and K3 such that that matrix equation holds. Okay, and for this to hold, we have a system of linear equations which got 3 unknowns. K1 is going to be an unknown, K2 and K3. And you're going to have how many equations? You're going to have 4 equations. All right, from there we get the matrix, given matrix. And again, I'm just going to quickly show that. So the first row of this matrix corresponds to that entry there. The second row corresponds to that entry there. Okay, the third row corresponds to that entry there. Okay, and the last row corresponds to that entry there. Okay. All right. All right. So we take our matrix, this one here, and we use Gaussian elimination. Take the first row and add it to the last row, and we get the new matrix there. And now what we're going to do is we're going to take -4 the third row and add that to the last row and get. Alright, and then we're going to take of that matrix, we're going to take twice the third row and we're going to add it to the second row and get. And then that we're going to take minus the last row and add it to the first row. Okay, and we're going to get. Okay, and then we're going to take the second row, multiply it with -1/2, and add that to the first row. Okay, and we get, right, so we get our final matrix. Now look at this. The first row gives me a clue as to what I need to choose for the values B, D, and C. Now this system is inconsistent, or it is consistent when this expression here is equal to 0. So to pick a vector that's outside of the span of my new set, we just need to make the system inconsistent. All right, so we can pick A as 0. We can pick B as 0. We can pick D as 0. And we can pick C as 1. And if I plug those values in there, we see that it's going to become an inconsistent linear system. So in that case, this vector here, A, B, C, D, is definitely not in the span of my vector set, my original vector set S union with that other matrix that I chose in the beginning. Alright, so by the plus minus theorem we can throw this vector into my set, and that is going to be linearly independent. Okay, so my basis is the set S, which is basically the two matrices 1, 2, 0, minus 1 and 0, minus 2, 1, 4. Added to that the two matrices, that one, and that set has got 4 vectors. It's linearly independent, and so it will be a basis. Alright, that brings us to Theorem 6. This theorem says if W is a subspace of a finite dimensional vector space, then number 1, W is finite dimensional. Number 2, the dimension of W is less than or equal to the dimension of V, and the only way that the set V and W can be the same is if their dimensions are the same. So quickly look at the first one. Why is it that if W is a subspace of a finite dimensional vector space, why is it then that the subspace inherits the finite dimensional property from the space V? Alright, so we take a subspace W of V, and we take a basis for V, which has got n vectors, and we said V is finite dimensional. Alright, so we claim the following: no set of fewer than n vectors in W can be linearly independent. Alright, let's prove this. Okay, so we start off by, we take W and we take a set W prime of I vectors, such that I is strictly less than n, and W prime is linearly independent. So let's say we can find a set of fewer than n vectors that is linearly independent. And we make sure that we choose I as large as possible. Right, okay. So what we do now is we assume the following. Now, if it happens that the smaller set W spans the capital W, then W prime, if it happens that the span of W prime is W, then W prime is a basis of W. And that's going to mean that W is finite dimensional because W prime has got I vectors in it, and I is strictly less than n. And remember, we said W prime is linearly independent, and if it spans W, then we are done. So we may assume that the span of W prime is not W. Alright, so we know that because it doesn't span it, there must be a vector in W, call it W, such that W is not in the span of W prime. Okay, so what does that mean? Right, so by the plus minus theorem, we can go and add W to W prime. Okay, and that is going to be a linearly independent set. Now, if this I is less than or equal to n minus 2, then this set here is going to have fewer than n vectors. Alright, so it's got fewer than n elements, and also W added to W prime is going to be larger than W prime. And it's a contradiction. Remember, we chose W prime to be the largest linearly independent set in the subspace W. But now I've found an even larger set, which is the set W prime added to that W. So you're going to have that set is still linearly independent, and it's got fewer than n vectors, and it is going to be larger than I, and that's going to contradict the way that we chose our original set W prime. Okay, so we may assume that I is not less than or equal to n minus 2. It is equal to n minus 1. So therefore, this set here is going to have n vectors in it. And it's going to be a linearly independent set. Okay, so what does that mean? What that means is it follows that the set W prime union W, we know it is linearly independent, it's got n elements, and we know that any set of vectors that's got n elements in a vector space that's n-dimensional, we know that that set must immediately, if it's linearly independent, must be a basis for the whole of V. So this set here is a basis for V. And so it must also be a basis for W, because this is contained in W, and therefore it spans W. So that is going to imply that W is finite dimensional. Right, so we proved our claim, and our claim was that the set W, if you take any a subset of W of fewer than n vectors, then that chosen subset can never be linearly independent. Okay, so let's just prove our statement, which is that W is finite dimensional, and the dimension of W is less than or equal to the dimension of V. Alright, so now if W is only the zero vector, then we know by definition the dimension of W is 0. And therefore W has finite dimension. So W is finite dimensional. And obviously the dimension of W is less than or equal to the dimension of V. So we may assume that W is not only the zero vector, so W has a non-zero vector. Right, so W has a non-zero vector. Let's call that vector, let's call it W, okay? Alright, so what happens if the dimension of V is at least 2? That means that N is at least 2, and we contradict our claim. Now, why are we contradicting our claim? What claim are we contradicting? That's the question. What claim are we contradicting? Alright, remember this claim here. This claim, we said that no set of fewer than n vectors in W can be linearly independent. Okay? Now, if we take the non-zero vector W and we make that our set in capital W, now, a set that contains one non-zero vector is obviously linearly independent, and therefore we contradict our claim by just taking our set as this W, because that's a linearly independent set that's got fewer than n vectors that's linearly independent. So we contradict this claim clearly. So therefore, what can we then say? Right, so we can then say that n is 1. Well, we can look at the case where n is equal to 1, and if the case of n, in the case of n equals 1, we have that the basis contains only one vector v, and therefore there's a vector v that spans the whole capital V. And that means that every vector in V is a linear combination of, or is a scalar multiple of this vector. It's a scalar multiple of that vector. Right, so what does it mean? We know that because the vector v spans the whole space capital V, we know that every vector in W can be written as a scalar multiple of the vector v, right? So we can basically say there exists a scalar k such that we can write W as a scalar multiple of the vector v, and because W is a non-zero vector, it means the scalar must be non-zero, so we can easily see that v must be a scalar multiple of W. So therefore, this is going to imply that v must be in the subspace W, because for v to be in the subspace W, it must be a linear combination of well, if a vector is a scalar multiple, in this case v, if v is a scalar multiple of a vector in capital W, then that vector is going to be in capital W, because capital W is closed under scalar multiplication. So hence the span of v, because v is in capital W, the span of v is going to be the whole of capital W, because v spans the whole vector space V, right? Okay, so it's going to mean that W is finite dimensional, and the dimension of W is less than or equal to the dimension of V. Okay, so the dimension of W is going to be at most 1. All right, and if n is 0, in other words, the dimension of V is 0, then obviously the dimension of W will be the same as the dimension of V. Because if V is the 0 vector, then W will be the 0 vector as well. All right, so the other two properties, I can refer you to the textbook to go and look at the derivation of that. All right, so the next section is somewhat of a tutorial, a few extra exercises. I'm going to leave exercise 1 for you guys to do and exercise 3. I quickly just want to look at exercise 2. Here they ask me to characterize whether a given set is a basis for a finite dimensional space using determinants. Okay, so depending on what the vectors look like, I want you guys to go and think back again to all the theorems we've looked at. In a finite dimensional vector space, all I need to check for a set to be a basis is whether that set is linearly independent or whether that set spans V. So essentially, all I need to actually check is the linearly independence. So if I can, establish when will linearly independence, when that property will hold, then I will be able to answer the question. All right, so let's take finite dimensional vector space V, and let's take an arbitrary set of n vectors. All right, so there we've got our set. Okay, and when is that set a basis? It's a basis if and only if what happens? If and only if S is linearly independent. That's all I need to check, because it's finite dimensional. Alright, and when is S linearly independent? It's linearly independent if that holds. In other words, setting up that equation only has the trivial solution. Alright, and the only way that can happen is if the following holds. The system L generated by this equation, the one we talked about just now, this one here, that one there, has the trivial solution. This is the linear system L. So remember, from here you're going to get a linear system of equations. You're going to set up a linear system with n unknowns and a certain number of equations. And you're going to solve that system, And if that system has a trivial solution, then it's linearly independent. And what needs to happen for that to be true? Right, we need the following. Right, what needs to happen then is this. The only way that can happen is if the matrix equation generated by L, so if you're going to take the system of linear equations L, and you set up the matrix equation generated by that linear system, which is this matrix equation here, okay, as the trivial solution. And the only way that can have the trivial solution is if A is invertible. All right, and the only way that can happen is if the determinant of A is not equal to 0. So therefore, A is invertible. All right, so that's your characterization. Setting up your matrix equation from your linear system. The linear system that you get from this equation here, the coefficient matrix A needs to be invertible. Then this system here will have the trivial solution only, and that only happens when the determinant of A